Okay, nice.
Antioch was run down with a broken simulation in parallel. Boston turns that fleet into a self-improvement loop. The SO-101 senses the sea, reasons over the task and constraints, and acts in simulation. Every rollout is stored in simulated directory. Failures become evidence. Evidence becomes the next candidate batch. Same task, same test, better than every improvement, replayable.
Okay, so that 3D simulation will be relevant in the future. But basically, we solved RSI. No, I'm joking. But we did solve two very outstanding problems that happened when, you know, the Antiochs of the world and the Nebiuses of the world like make compute and running inference for robotics models a lot more available. And those two problems are, number one, defining what the actual problem you want to solve. So VLA, VLMs are used to solve very specific problems, but these specific problems are very hard to describe with just text, right? And the second problem is like the output of the VLA, VLM, how do I judge that on a criterion? What's my evals, right? And then, funnily enough, you have those two, you can turn it into a loop and have it improve itself, or improve itself to a degree, not RSI degree, but improve until you get more servers solved. So with that said, let's get into it. So number one, this is kind of the run. Let's start a new run, and this is kind of the pre-built scene. So here we have an SO-101 arm, and then we have two cups. Now the goal is I want to put one cup in another, but I want to define, you know, this problem. So let's make it a little harder and put it here, right? Now hit the review start. Yes, I want to do that. And then this is the motion. So this is the prompt that will probably feed the model. So I want to pick up cup A, move it in an arc over cup B, and then slowly lower it until it's in there. So let's now generate the motion. And it'll call in an Opus 5 sub-agent. Now Opus 5 is actually really good at 3D. So the video that you saw at the start, that was using the same kind of 3D harness as the one here. So boom, it shows that with the motion profile. Okay, super cool, let's accept that draft. But I still want to make one more change. So let's go into refining this motion, and let's say I want to make the arc higher, right? Boom, generate. And now it's going to generate, give it a second for Opus 5, you know. And now I can open up the motion preview, and boom, it's actually made that arc a bit higher. So me having to describe this, I want it kind of like this kind of curve, it's hard to do that. So that just makes it 3D. So now that we have our like actual target, how do we hit it? Which is...
Exactly. So what we're trying to do here is we utilize small VLA to essentially do the task which we essentially planned out through visualization and essentially talking with a simple UI. So literally anyone can do it. So what you do is we have our small VLA, it does the task, and what we realized was in between for one of the tasks, this is the simplest task we could think of, by the way, was picking up a block. And the model failed. Small VLA has 450 parameters, and what it's trying to do is trying to like pick up the block by like putting the grippers on top of it. And iteratively I was like, okay, this is like not gonna work, we should like do some prompt engineering. So I was like, why don't we automate this process itself? So what we did was we set up a loop where essentially small VLA has 5 simulated runs with 10 runs each in each sub-simulation essentially, so 50 runs. And what we try to do is from the 50 runs, if there's a 0% success rate, then there's a wall, right? Like you can't just keep fine-tuning failure, you're just gonna fail more. So what we did is that's where Claude comes in. We essentially take all the data, packaged it, and Claude Code interacted with Antioch to essentially figure out what the problems was and then modify the problem. So this was, let's see. Yeah, where's the, okay. Where's this? It's like, yeah, this is okay, oh yeah, that's it. Yeah, okay, cool. Wait, my bad. So it's essentially what it did was it decided to rewrite the prompt so it was easier for the VLA to understand. So this was the initial prompt. Graph the red cube and lift it 10 centimeters. So first iteration lands at 0 to 50, that's the issue. So Claude Opus rewrote the prompt to open the gripper above the cube, close the gripper on the cube, lift the cube up by 10 centimeters. So we wanted to automate the full process itself, where we have a small 450 million parameter as like the main workhorse, and a large model being able to teach and like correct it whenever needed. So once that model was in, so the instructor rewrote the prompt and we were able to get relative success. So this is one of our successful runs actually. So this is utilizing small VLA, which is fine-tuned using low rank adaptation. Can we play this? Okay, yeah. anyways, it works, right? So this was like one of our successful runs after I think around 9 training samples. One of the cool things was since this was such a small model, we were able to do really quick iterations. We had around I think 800 to 800 parameters for each like sub-training, so it was really quick. And that was the general idea, right? You essentially train it and keep iterating. One of the cool things actually, so I took a minute to analyze and see if we were able to meet certain requirements. And when we hit the 0 to 50 failures, what I did was, okay, let's set some sub-goals. So Claude literally like pulled up some, okay, these are some sub-goals. We have to achieve this to like achieve the bigger goal of lifting up the cube, and it checked all of these things with the successful run. And again, we log all of the data, right? The cube height, how much it moves, how much the gripper opens, all the joint estimations, all of these things. We also looked at the failure cases, like in certain failures, did the record demonstration lift the cube in the seam? No, it didn't. Okay, so that's the failure, like why is it not doing that? So Claude has no context. We just don't want to burn tokens as well. Look at the Antioch side. This was one of our failures. So let's see. Yeah, so this was one of our failure runs where the model sort of like tried to grasp it, but it missed. I feel like maybe the camera angle was off or something like that. But essentially, what we're trying to do is we're trying to automate the process of fine-tuning for really specific tasks, right? Construction work, factory work, and just like optimizing it so that people don't have to be there. You don't have to be that skilled to essentially like work with a VLA, prompt all this, work with it, and you essentially have like a super intelligent model working with a simple small VLA to complete the task and automate the process. So that was our project, automating task completion utilizing VLA. Thank you.
Questions from the participants? No?
Happy to take questions. We love questions. Please. Yes.
I'm curious how you guys and kind of like the dashboard you guys built out and that experience, like how you hooked into Antioch, how you effectively compiled and aggregated the data and the metrics coming from the scenario outputs, how you went about doing that.
Definitely. So when Antioch first, when y'all came up and talked about Antioch, one of the first things I noticed was, do you have Cloud Code, Codex integrations, right? And that was really interesting to me because then what happens is not only can we set up automation loops, our agents can automatically analyze, pull the data, and look at it and properly collect the data and analyze. So what we did is the agent is the middle layer between the website and Antioch. So we're trying to see, maybe it's something we could collaborate on, maybe an MCP line between Antioch and directly to our website. But looking into the extensions of this, that's something we wanted to do. We wanted to set this up to be completely free, where users can put in their own API keys. We're not millionaires, so we just used our Cloud Code credits, our API program to do this. But essentially, users have it for free. They can put the API credits and use our own system, essentially. So what we did is we built the harness so people could do that. Thank you.
One more question. Did you experiment at all with fanning out simulation runs? So obviously it's the loop is somewhat predicated on being able to run many of these policy eval sessions and driving that feedback loop as much as possible, as quickly as possible, hence why having a smaller VLA model makes a lot of sense. Did you experiment at all with fanning out simulation runs across many GPUs and kind of parallelizing some of that process?
Definitely, yeah. I believe we tried doing this. I believe we did this on Antioch itself. We set up 10 simulated runs to run simultaneously. I believe so, yeah. One of the other things we also did try was using Groot 1.7, and there was another model which was trained purely in SO101 data. But those are 3 billion and 8 billion parameter models, and training it would take really long. So the training, we actually thankfully had access to my university GPU, so I was able to do LoRa fine tuning on those and use your GPU computing to run the simulations itself. Yeah, thank you so much. Cool, thank you.
Thank you so much. Hey, thank you again for all